Welcome to Study Loop.
All right. So we have 4-bromo 2-hexene. So 2-hexene means a double bond between bonds 2 and 3. That means this is carbon 4. So this is where bromine can go. And you'll notice that there's an E and a C version of this. So what we're going to end up with is 4 possible enantiomers, right? There's E, Z, and then there's R, S. Okay. So let's just start with this basic. Okay. So if we want Z, it's going to look like that. And if we want E, it's going to look like that. Okay, now we can do a wedge to bromine, or we can do a dash to bromine. Same here, we can do a wedge to bromine, or we can do a dash to bromine. Okay. Now, which is R and which is S? Bromine is the highest priority. Next highest priority is this carbon that's got 2 bonds to carbon, then this carbon that only has a single bond to carbon, and hydrogen, lowest priority, is in the back, number 4. This is 1, 2, 3 counterclockwise, which means this corresponds to S. And that makes this R, which makes, and then this, as we said, is Z, and this is E. Okay. There we are. Okay. That's all the different possible isomers of 4-bromo 2-hexene. Now we need to draw a reaction coordinate diagram for an endothermic reaction that occurs in 5 steps, with the third step being rate limiting. Okay. So reaction coordinate diagram, we're going to need axes. Let's put delta G. And this is going to be our reaction. Well, I can draw a little straight on that. This is our reaction coordinate. Okay, so what information do we know? It's 5 steps. That means 5 transition states. We've got a endothermic reaction. So I guess that means this is delta H, not delta G. Endothermic, it's going to mean that our product has a higher energy than our starting material. So let's just put our starting material down here, label it SM, and our product must be some higher energy. Okay. Now they're saying 5 steps, which means 5 transition states, which is kind of insane. I'm guessing they probably mean like 2 transition states, right? And that's what they mean by 5 steps. We could do it both ways. I don't know. No, because then how could the third step be rate limiting? Because then it'd be 1, 2, 3. It wouldn't. Yeah. No. This is what they're looking for. Okay. So we need 5 transition states, which means we're going to need 5 peaks in between the starting material and the product. So 1, 2, 3, 4, 5. The other thing we need, I mean, there's really no telling whether any of these should be higher or lower, right? It doesn't really matter, because what matters is that the third step, the one for TS3, that the barrier for getting to TS3 is higher than any other barrier. So that just means if we put the intermediate down here, for example, right, that none of the other intermediates can have this low of energy. That's all. So we can just do this. I mean, it's pretty unrealistic, but it meets the criteria. This is the highest barrier. I guess that's not true because we need that would make this barrier. So we can do this. We just have to make one little alteration. And that's that. We need to raise up the energy of the starting material a little bit. And we should probably lower the energy of TS1 so that the barrier for TS1 is not as high as the barrier from intermediate 2 to TS3. And there we are. This would be a perfectly valid 5-step reaction coordinate diagram, which is endothermic and has a rate determining step of step 3.